All right, so we're diving into AI safety and reliability,
Mm.
and we've been talking about how well models generalize to new data,
Hmm.
and that's obviously super important. But there's this whole other layer, like reliability in the actual training process itself.
Yeah.
It's kind of like building a house.
Oh, absolutely.
You need a solid foundation.
Yeah. A beautiful blueprint is useless if the foundation is shaky. And this paper, Data-Aware Training Quality Monitoring and Certification for Reliable Deep Learning, that's exactly what they're getting at. They introduce this concept of YS bounds
Okay.
to assess if a neural network is truly learning effectively from the data.
So is this like a pass-fail system for AI training? How does this work?
Think of it as a data-driven method for answering a really fundamental question. Is this training process itself reliable? And so, the paper argues that traditional methods often just focus on these narrow aspects of optimization, like just is the loss function, decreasing smoothly? But that doesn't necessarily tell us if the AI is actually learning the underlying patterns in the data.
It's like checking if a student can just memorize answers for a test,
Right.
but they don't actually understand the concept.
Exactly.
Just because they get an A doesn't mean they actually learn the material.
And that's where YS bounds come in. They go beyond those local metrics and provide a more holistic view of the training quality. Instead of just looking at individual steps, they're analyzing the entire training trajectory in relation to the data itself.
Okay, so how do they actually measure this training trajectory? It sounds kind of abstract.
So imagine you're trying to reach destination. A simple approach might be to just try to get there in one giant leap.
Mm-hmm.
That's essentially what the yes-Laro bound does.
Okay.
It sets a baseline by just assuming no intermediate steps.
So it's like measuring the shortest possible distance between the start and the goal.
Exactly. And then we have higher degree YS bounds, which get more sophisticated. They consider strategically chosen intermediate points based on the structure of the data. And these points represent key milestones in the learning process.
So instead of one giant leap, we're now looking at a series of smaller, more strategic steps and making sure the AI is hitting those milestones along the way.
Yes, and the key is that these milestones are not arbitrary. They're determined by the data itself,
Okay.
ensuring that they reflect the specific task that the AI is learning.
That makes sense. So these YS bounds are kind of like checkpoints, evaluating if the AI is effectively navigating this path carved out by the data itself.
Precisely. And this is where it gets interesting. YS bounds can spot suboptimal training even when traditional methods are fooled. The paper gives examples where the training loss plateaus, seemingly indicating that the model is converging.
But the SS bounds are saying, hold on, you're not really learning effectively, you're stuck.
Exactly. Traditional methods might be fooled by that plateau in the loss function, but YS bounds are looking at the bigger picture, considering the data and the overall learning process.
So this is highlighting that AI reliability isn't just about the final performance of the model. It starts with ensuring that the training process itself is robust and reliable.
Absolutely. And that's why this work is so crucial. If the training itself isn't reliable, we can't trust the resulting model to make sound decisions.
Okay, this is really fascinating. I'm curious to hear more about how these WES bounds are actually integrated into the training process.
Well, the authors introduced this really cool visual tool called the Training Cloud.
Okay.
It's a color-coded system that lets you monitor training in real time.
So like a traffic light for AI training.
Exactly. Red means ineffective, yellow means caution, and green means you're on the right track.
Okay, now I really want to see this in action.
Right.
Can you give us an example of how this training cloud and these WES bounds translate to real-world results?
Sure. The paper demonstrates the concept using an image denoising example. And they show how the recovered image quality improves as training progresses through the different cloud zones, directly correlating with the YES bounds analysis.
So we're not just talking about some abstract theoretical concept. Yes, as bounds have a tangible impact on real-world performance. That's incredible. But does this mean we can use YS bounds to actually guide the training process itself? Could we adjust the model based on the feedback from the YS bounds?
That's a great question, and that's where things get a bit tricky. It might seem intuitive to, directly adjust the model based on that YS bound feedback, but the authors caution against this.
Why is that? Wouldn't real-time adjustments lead to more efficient training?
Imagine giving a student the answer key during an exam.
Uh-huh.
Sure, they would ace it, but would they actually understand the material?
Right.
We want the AI to learn from the data, not from hints or shortcuts.
That makes sense. We want authentic learning, not just good scores. So how can we harness these YS-bound insights without compromising the AI's learning process?
Think of it more like a coach guiding an athlete.
Right.
They observe the performance and they offer feedback, but they don't dictate every movement. The paper suggests using YS-bound analysis to guide things like learning rate adjustments.
So we're not telling the AI what to learn, but we're maybe kind of hinting at how fast it should be learning.
Exactly. If the YS bounds indicate that the model is struggling, we might want to, slow down the learning rate to allow for a deeper understanding of the concepts. Conversely, if it's progressing really well, we might increase the rate to accelerate learning.
It's fascinating how ESS bounds kind of shift our perspective on AI training. We're not just focused on the final output, but we're also thinking about the journey of learning itself.
Absolutely. And this brings us back to that core issue of reliability. If the learning process itself is flawed, even a seemingly high-performing model might be unreliable.
Right, because it could be making decisions based on like superficial patterns or shortcuts,
Right.
rather than a true understanding of the data.
Precisely. And that's why this focus on training reliability is so crucial for building AI systems we can actually trust.
Okay, I want to go back to those different degrees of YS bounds for a moment.
Right.
You mentioned YS0 as that giant leap approach, but then there's these higher degree bounds that get more sophisticated. Can you unpack that a bit more?
Sure. Remember, YS0 essentially measures the shortest possible path to the goal, assuming no intermediate steps.
Uh-huh.
But real learning rarely happens in one giant leap. It's a gradual process of building understanding.
Like learning a new language.
Right.
You don't become fluent overnight. It takes time. Practice mastering different aspects of the language.
Exactly. Higher degree IS bounds acknowledge that complexity. They incorporate strategically chosen intermediate points, those milestones we talked about,
Yeah.
that represent key stages in the learning process.
So instead of one giant leap, we're looking at a series of smaller, more deliberate steps.
Precisely. And remember, these intermediate points are not random.
Right.
They're determined by the structure of the data itself.
Right. So if we're training an AI to identify different species of birds, those milestones might be recognizing beak shapes, wing patterns, or specific bird songs.
Exactly. By analyzing how well the AI is hitting those data-driven milestones, higher degree YS bounds offer a more nuanced and accurate assessment of its learning progress.
This highlights how the data itself is not just fuel for the AI, but it's also a guide for its learning journey.
It's a beautiful synergy, really. The data informs the training process, and the YS bounds, in turn, use that data to evaluate how effectively the AI is learning.
This makes me wonder, how do we actually choose those intermediate points for those higher degree YS bounds? Is it a manual process, or is there a way to automate it?
That's a great question. The paper proposes two main approaches. One is problem-specific construction, where experts use their knowledge of the task to handpick those milestones.
So if we're training an AI to play chess, those milestones might involve recognizing opening strategies, evaluating board positions, planning sequences of moves.
Exactly. This works well when we have, a deep understanding of the task and the steps involved in mastering it. But what about tasks where we don't have that level of expertise? What if we're venturing into uncharted territory?
That's where things get even more exciting, right?
Absolutely. That's where the second approach comes in, using the training data itself to guide the selection of those intermediate points.
So we're letting the data tell us what the important milestones are.
Precisely. This leverages the power of deep learning to discover those crucial steps in the learning process, even those we might not even be aware of.
This all sounds incredibly promising, but I'm sure, like any tool, YS bounds have their limitations. Are there situations where they might not be applicable, or they could provide like misleading results?
That's a critical question. One thing to remember is that YS bounds are based on certain assumptions about the structure of the data in the learning process. If those assumptions don't hold true, the results might not be as reliable.
It's like using a map of Paris to navigate London. The basic principles might be similar, but the specifics won't match.
Exactly. And it's important to note that YS bounds primarily focus on the training process itself.
Okay.
They don't actually guarantee how well the AI will generalize to new unseen data.
So even if an AI gets a perfect score on its training data, there's no guarantee it will perform well in real-world scenarios.
That's right. Generalization is a separate, though related challenge in AI, and it requires its own set of tools and techniques.
This makes me wonder if YS bounds can be applied to all types of AI models, or if they're kind of specific to certain architectures.
That's a great point, and it's an area where more research is needed.
Yeah.
The current paper focuses on specific types of neural networks, but it's not clear how well YS bounds would work for other architectures like recurrent neural networks or transformers.
Those were like the powerhouses behind natural language processing and some of the most advanced AI applications today.
Exactly. It would be fascinating to see how YS bounds could be adapted or extended to work with these more complex architectures.
This entire conversation has been a revelation. Yes, bounds seem to be a game changer for AI training and reliability. But before we get too carried away, let's zoom out a bit and consider the bigger picture. What does all this mean for the future of AI? How will yes bounds shape the way we develop and interact with intelligent systems?
That's a profound question, and it's one that researchers and developers are actively exploring. One potential impact is that yes bounds could become a standard part of AI development, similar to how we use unit testing or code reviews in software engineering.
So it's like adding another layer of quality control, ensuring that our AI systems are built on a solid foundation of reliable training.
Exactly. Imagine a future where every AI model comes with a YS bound certificate,
Okay.
providing evidence that it has been trained effectively and reliably.
That would certainly go a long way in building trust in AI, not just amongst experts, but also within the general public. But beyond certification, what other possibilities do you see?
Well, as we delve deeper into the capabilities of YS bounds, I believe they could lead to the development of entirely new training methods that are more efficient, robust, and data-aware.
So we're not just checking boxes. We're fundamentally changing how we approach AI development itself.
Precisely. And who knows, as we continue to research and experiment, we might uncover even more applications and insights that we haven't even begun to imagine.
Okay, this is all incredibly exciting, but I do have one final burning question.
Mhm.
We've talked about the theoretical foundations of YS bounds, their practical applications, even their limitations. But at the end of the day, why do they work so well? What's that underlying principle that makes them so effective at evaluating AI training?
That's a fantastic question, and it might surprise you to learn that the answer lies in the clever use of heuristics.
Heuristics, you mean like rules of thumb or mental shortcuts?
Exactly.
Yeah.
Yes bounds are based on this idea that a well-trained AI should be able to outperform these simple linear projections of the data.
So it's kind of like establishing a baseline. If the AI was just blindly guessing, this is how well it would do. And if it performs better than that, it suggests that actual learning is taking place.
Precisely. Even the more sophisticated YS bounds, with their multiple intermediate points, are essentially heuristics. They're cleverly measuring how much the AI's performance exceeds that simple linear baseline.
So it's like saying if the AI was taking random steps, it would never reach the destination.
Right.
The fact that it's progressing, even if not perfectly, implies that it's learning something valuable.
That's a great way to put it. And the authors emphasize that YS bounds are a necessary condition for optimal training, but not a sufficient one.
Meaning just because an AI meets the YS-bound criteria doesn't automatically mean it's reached peak performance.
Exactly. There might be even better solutions out there. But exceeding those simple heuristics gives us confidence that the training is on the right track. It's like passing a series of increasingly difficult tests. It doesn't guarantee you'll ace the final exam, but it shows you're building those necessary skills.
I see. So YS bounds are like a safety net, ensuring the AI isn't completely off course during training.
That's a good analogy. And here's where it gets even more interesting. The authors point out that as training improves and the AI's performance gets closer to that optimal solution, the YS bounds themselves become less critical.
Because the gap between the AI's performance and the YS bound shrinks. The heuristic becomes less relevant as the AI moves beyond those basic benchmarks.
Precisely. It's like a student who has mastered the fundamentals and is now tackling these advanced problems where those initial heuristics no longer really apply.
So YS bounds are most valuable during those early stages of training, providing that crucial feedback and ensuring that the AI is on that path to success.
Exactly. And as the AI progresses, we can then shift our focus to other evaluation metrics and fine-tuning strategies.
This has been an incredible deep dive. YS bounds are clearly like a groundbreaking tool for AI training.
Yeah.
But like any powerful tool, they need to be used thoughtfully and carefully.
I completely agree. And the authors themselves emphasize the importance of transparency, reproducibility, and ethical considerations when using YS bounds. They're not just focused on advancing the technology, but also ensuring that it's used responsibly.
It's reassuring to know that the researchers behind this groundbreaking work are also deeply committed to those ethical implications. This kind of brings us to our listeners. We've covered a lot of ground today, from the technical intricacies of YS bounds to their potential impact on the future of AI. And what we really want to leave you with is this. As AI continues